Okay, so we'll start recording and we'll start our lecture. Okay, so today I'm going to talk a little bit more about regularization, and we will also talk about the bias variance trade-off. That's going to be our topic for the day. All right. So when we talked about regularization, we said regularization modifies the blank. OLS regression minimizes the, and then again, what is, blank function only, whereas the regularized loss function has the sum of squared errors plus a penalty for something blank, okay? And the fitted model will try to minimize both squared error and complexity, and the blank term is used to determine which goal has greater priority. So I don't know if you're filling in the blanks in your head here, but the answers to this are regularization modifies the loss function, or modifies the loss function, and ordinary least squares uses the squared errors only. Okay, that's its loss function. Okay, whereas regularization has a squared error plus a penalty for complexity. Okay, so when you fit regularized least squares, it's going to try to minimize both the squared errors and the complexity, and the lambda term is used to determine which of these goals has greater priority. Is it more important to minimize the squared errors, or is it more important to minimize the complexity? Okay, and so quick review. We said that I introduced LASSO and ridge regression, and both of these will use the vector of coefficients as some kind of measure of complexity. LASSO uses the absolute values of the vector of coefficients, so it takes the sum of the absolute values, and ridge regression takes the sum of the squared values as its measure of complexity. So in both of these cases, if you have a large W term, it's going to contribute more to the complexity measure, and smaller terms of W contribute less, right? And so for that reason, we almost always recommend centering and scaling your data prior to using it, or at least making sure all of your X terms are on the same kind of same scale there. Okay, and so there's something called elastic net. Okay, elastic net is a hybrid of LASSO and ridge regression. So LASSO uses the L1 norm, and ridge regression uses the L2 norm squared. Okay, and so what elastic net does is it uses both the L1 and L2 norms. Okay, except it does kind of it splits the difference. So there's an alpha term, okay, and alpha is going to range from 0 to 1. So if alpha is 0, okay, then it puts no weight on the LASSO, the L1 term, and if alpha is 0, then it's basically all the L2 norm. So elastic net with alpha equal to 0 is equivalent to ridge regression. On the other hand, if alpha equals 1, then there's no L2 norm for W, and all the weight is placed on W on the L1 norm. And so with alpha equal to 1, LASSO is equal to, elastic net is equal to LASSO, okay? And then you can pick something in between, such as, alpha equal to 1/2, and that's going to kind of split the difference, and the complexity parameter will be half L1 and half of the L2 norm, okay? And whatever this thing is, okay, whatever goes inside here, this is kind of our measure of complexity. There's still a lambda term to say, this is how important the complexity measure is versus the least squares measure, the regular old loss function from OLS. Okay, so it's still OLS least squares, or the squared error term, plus lambda times complexity. It's just complexity is now a blend between the L1 and the L2 norm, okay? And it's called ElasticNet. So there's a package for R called glmnet that implements ElasticNet. And because ElasticNet is basically, you can have LASSO with alpha equal to 1, you can have ridge regression with alpha equal to 0, and you can have stuff in between. That's how we would do LASSO or ridge regression. We wouldn't, well, I'm sure there's probably some package out there that does LASSO all by itself. But I would say probably glmnet, the ElasticNet is probably one of the more frequently used packages for implementing LASSO. Okay, and all right, and so this is just kind of a little paragraph taken straight from the vignette on the package glmnet, right? And so again, with LASSO, what we saw is that as that lambda term increases, as we say a larger penalty is placed on the complexity, what happens is that those coefficients get driven down to 0. Whereas with ridge regression, the coefficients rarely get driven all the way down to 0, but it will shrink them and will often shrink the coefficients towards each other. So it says, it is known that the ridge penalty shrinks the coefficients of correlated predictors towards each other, while the LASSO tends to pick one of them and discard the other, okay? As in, discard the others means pushes the other terms down to 0. The ElasticNet penalty mixes these two. If the predictors are correlated in groups and alpha equals to 0.5, and alpha equal to 0.5 tends to select the groups in or out together. This is a higher level parameter, and users might pick a value up front or experiment with a few different values, okay? And what we saw is that LASSO tends to push some of the coefficients down to 0, and so it can be used for variable selection in of itself. All right, and so to run glmnet, you would call library glmnet, okay? And then the fit, you would just fit your matrix of X, okay? So this is a little bit different from your normal LM function, okay? So you have your X predictors X, and that's gonna be your matrix here, and then you have your output Y, okay? And so you do glmnet X comma Y, and then you specify alpha. By default, alpha is equal to 1, okay? But you can change alpha anywhere from 0 to 0 to 1, okay? So with alpha equal to 1, remember the formula back here is with alpha equal to 1, all the complexity is determined entirely by the L1 norm, which is equivalent to LASSO, okay? And then if alpha was 0, all the complexity is determined by the L2 norm, which would make it equivalent to ridge regression. Okay, so to kind of illustrate how this works, I'm going to generate some artificial data, okay? So our artificial data is going to have 4 variables, 4 X variables, X1, X2, X3, X4, okay? And I'm making X1 and X2 correlated, okay, with a correlation of 0.8, and X3 and X4 are correlated with a correlation of 0.8, okay? And that's, this data is being generated using library multivariate norm, okay, and I'm using RMV norm to generate these correlated values, okay? Or actually, I guess I used 0.85. Sorry, I got to fix that. X1 is independent of X3 and X4, and X2 is also independent of X3 and X4, which also means X3 and X4 are independent of X1 and X2, okay? But clearly X1 and X2 are correlated with each other, and X3 and X4 are correlated with each other. And what I've done here is, so I put those together in my X matrix here using cbind, and here I'm generating the true value of Y. The true value of Y is found by taking 3 times the X1 variable minus 1.8 times the X3 variable, okay? The true value of Y does not depend on X2, It does not depend on x4, okay? It's just that x2 is correlated with x1 and x4 is correlated with x3, okay? But the true value only depends on x1 and x3, okay? And so this could be a situation that, you know, could make, could give ordinary least squares a little bit of trouble, right? When you have correlated predictors, sometimes the standard errors on your coefficient terms get large. Okay, so anyway, that's the true relationship to y. And what I've done is I've used our norm to just generate error, and I'm going to add random noise to the true y, and this is going to be our observed y. Okay, so our observed y is the true y values plus some error. Okay, and the true y's are determined only by x1 and x3. So this is what my artificial data looks like. Okay. Oh, here, let me give you the answer to the first quiz question. First quiz question has answer E as an elephant. E as an elephant. That's going to be quiz question 1 for today. Okay, are we good on the generation of data here? Any issues or questions? Okay, so we're going to use glmnet to fit, and I'm going to say do glmnet x comma y alpha equals 1. So this is going to do a lasso. All right, so we're going to do a lasso fit to the data, and this is what the results are. So when you run lasso using glmnet, this is the results, and you get these 3 columns of data and probably like 60 rows or something. Okay. And it starts off, the 3 columns are df, percent deviation, and lambda, okay? So df is the degrees of freedom used in the resulting model, okay? So it starts off with a large lambda, and the lambda goes down. So when you have a large lambda, what that means is you are penalizing the complexity factor by a lot, okay? So let me zoom in a tiny bit. Okay, so with a large lambda, we're penalizing the complexity, and so a large lambda is going to favor a simple model. In this case, a large lambda has pushed all the coefficients down to 0. Okay, it's pushed all the coefficients down to 0, and so what we're basically doing is we're predicting no coefficient terms for the x variables. Okay, and so we are able to explain 0% of the variation. Basically, we're fitting a flat line, okay? We're fitting basically the mean of y to the data, and so we're able to explain 0% of the variation, right? The SS regression divided by SS total is going to be 0, SS regression 0. Okay, when I reduce the lambda, now I have a coefficient for one of the x terms, okay? And if I and so I have, so this is equivalent to having 1 term in our model, okay? Degrees of freedom, right? As you increase the number of parameters in your model, the degrees of freedom goes up, okay? And so the degrees of freedom is kind of equivalent to how many terms you have in your model, okay? And so as I decrease my lambda, I'm able to increase the coefficient for that particular x variable, and I'm able to explain some of the variation, okay? As I increase my lambda more, my coefficient's able to get larger, and I'm able to explain more and more of the variation in y, okay? And as lambda continues to go down, I'm able to explain more and more of the variation, okay? And the degrees of freedom, now it jumps from 1 to 2. Now we're gonna have 2 terms in the model, okay? And as it continues, eventually we'll add in a 3rd term, and then all 4 terms, okay, as lambda decreases from a large number down to a small number. Okay, and I've written this all out, okay? So each additional parameter that you estimate uses an additional degree of freedom. That's what that first column is. The middle column is the percentage of deviation explained. That's equivalent to the model's R squared value, or sum of squares regression divided by sum of squares total. and the last column is the lambda term, right? So when lambda is large, this pushes all the coefficients to 0, and we have degrees of freedom equal to 0, okay? And as lambda decreases, models are punished less for complexity. This allows the model to incorporate more terms, all right? And if lambda reaches 0, then no regularization is applied, and the model coefficients would be equivalent to the OLS model coefficients. So just for comparison, I ran ordinary least squares, okay? So I did linear model y tilde x, and then we asked for the summary here. And, oh, I'm sorry, you know, I updated the model, okay? But the R squared value here is 0.954, okay? The R squared value is 0.954. And take a note of the coefficients. The coefficients for the x1 through x4 start off at 3.04, negative 0.01, negative 1.84, and 0.05, okay? And OLS correctly identifies that only the x1 and x3 terms are significant, okay? So let me just show you, so this is the OLS coefficients, and let me show you the effect of changing the lambda, okay? So when lambda is equal to 0, remember, the LASSO is, the coefficients in LASSO are going to be equivalent to the OLS estimates, okay? And so we were able to, with OLS, our R squared value is 0.954, and so with lambda equal to 0, our R squared is also 0.954. As I increase my lambda, I'm changing my coefficients to be smaller, and so my R squared value will go down, okay? Until it reaches 0, until all the coefficients are 0, right? And so you might say, well, why would we even want to do this? Why would I intentionally shrink my coefficients to a smaller value so that my R squared value goes down, right? This seems self-defeating, right? Like, why would I do LASSO? Okay, if OLS gives me the highest R squared, and increasing lambda causes my R squared to go down, causes my coefficients to shrink towards 0, it seems like I shouldn't do this, right? So I'll explain why we would do this in the first place, but here are some pictures here. Okay, so this just shows the effect of increasing your lambda and its effect on your R squared value, okay? And so it kind of drops off until it reaches 0. Okay, the coefficients themselves are estimated and stored in this matrix matrix here, okay? And it's technically a sparse matrix. And so, so this starts off with, you're gonna read these columns from left to right, okay? So when we have a very large lambda, okay, all of your coefficients are 0, okay? And a sparse matrix basically means if it's a 0, it just puts in a dot, okay? It doesn't actually store the 0. You can get the zeros in there if you like by calling just as matrix, okay? Otherwise, it'll call print sparse matrix. And so with lambda equal to the big number, that's our kind of our first model here, all of our coefficients are 0. As lambda decreases, okay, as we move to the right, okay, each of these columns represents a different value of lambda and different coefficients that it estimates, okay? So as we move to the right, we're decreasing our lambda, and we can see our coefficient for the different variables start to increase, okay? So by the time I've decreased my lambda, I guess the 4th time, I have a larger coefficient for variable 1 and a coefficient for variable 3, okay? And as I continue to decrease lambda, my coefficients get larger and larger, okay? Because the amount I'm penalizing goes down, okay? And this would continue. It looks like it fit maybe 55 different models, okay? And so remember, at the very end, so this is lambda very close to 0. It's not quite 0, okay? But it's very close to 0. And it says V1 should be 3.016, and variable 3 or x3 should have a coefficient of negative 1.785, okay? Whereas if we had shrunk lambda all the way to 0, we would get the OLS terms, okay? The OLS terms are 3.04, negative 1.84, and then a small value for x2 and a small value for x4, okay? With lambda equal to, not quite 0, but small, it has still pushed the coefficients for x2 and x4 down to 0, okay? And so, this is where we are here. If you don't have to print out this whole matrix, okay? If you just want, okay, what are the coefficients when I've got lambda equal to 0.2, or what are the coefficients if I've got lambda equal to 1, okay? You can call those things as well, okay? So, and what we see is that when lambda is bigger, the coefficients are smaller, right? Because LASSO says the size of the coefficients themselves are an indicator of how complex the model is. And so a larger lambda is going to favor smaller coefficients. And so, so here with lambda 0.2, we got 2.83 and negative 1.63. And then with lambda equal to 1, I've got 2.036 and negative 0.953, okay? And glmnet also features kind of built-in cross-validation, okay? And with cross-validation, what it does is, it does like k-fold, or here I said do 5 folds or whatever, cross-validation, and here it creates this plot estimates the mean squared error, okay? And what we can see is that when lambda is large, okay, our mean squared error is huge, okay? Because when lambda equal to large, it's basically going to fit no coefficients there, right? All the coefficients will get pushed down to 0. As lambda shrinks, okay, as lambda gets smaller, it's going to approach the OLS estimates, okay? And it's hard to see, but the mean squared error goes down, and it actually comes back ever so slightly. Like this end is a tiny bit higher than some minimum value in the middle here, okay? It's really hard to see, but in this plot. But the left-hand side is a tiny bit higher than some value in the middle here, okay? Probably the lowest is somewhere around here. And basically, this is what we're saying is that, you know what, when you go down to the OLS estimates, you actually get a slightly higher mean squared error, right? And so you can actually ask, what was the value of lambda that produced the smallest mean squared error when we did cross-validation, okay? And it says the value of lambda was not 0, it's not the OLS estimates, but it's 0.05, okay? And if you fit 0.05, then the estimates it would get would be 2.98 and negative 1.758, right? There's another value, okay? And that's actually this column right here. I know there's a faint line here, and this corresponds to the minimum lambda. And then there's also one called lambda.1se, okay? Lambda.1se is going to be the right side bound here, okay? And that is the largest value of lambda, okay? It's the largest value of lambda that's still within 1 standard error of the minimum value of lambda. So this is the smallest value. This is the lambda that produced the minimum, and this is the largest lambda that produced an error that's still within 1 standard error, okay? And we can see, the lambda is a little bit larger, so my coefficients are a little bit smaller. Okay, but again, you might have this question and you say, well, OLS produces R squared of 0.954, and as I increase lambda, it just causes my R squared to go down. So why would I even want to do something like this, right? So this is, so we're going to talk about the benefits of regularization here, okay? All right, and so what we have to keep in mind is that our observed data is a random sample drawn from the population, okay? And so, so the coefficient estimates that we get, whether from OLS or some other system, is that those coefficient estimates are subject to the kind of the random noise or the random sampling process from the from selecting values from the population, right? So, you know, we've selected values from the population and we fit some kind of model to it. If we had gone to the population and drawn a different random sample, we might fit different values to it, okay? And so, so these coefficient estimates, you know, the slope, the intercept, your W1, W2, W3 terms, those are all, they all have a sampling distribution, okay? Indicating that, you know, if we took different random samples, we would get different coefficient estimates. And so I think in 100B, you talk about how OLS is the BLUE, the blue, the best linear unbiased estimators. Is that right? You guys covered this concept? Okay. Okay, you prove it in 100C. Okay, so this is a topic from 100C then. Okay, and what this means is that the coefficient estimates of OLS are unbiased, right? Which means that in the long run, when you take different random samples, when you do find the OLS coefficients, that in the long run, the average, the expected value of those OLS coefficients will tend towards the actual coefficient that might exist in the population, all right? And when we talk about best here, it means that you have the lowest amount of variance among all of the other unbiased estimates, right? This is what, Gauss-Markov theorem or something like that. And so this is, but there is a known issue with ordinary least squares regression, okay? And it's that if you have variables that are highly correlated, the coefficients of those variables exhibit high variance, right? Because sometimes the model will say, you know what, I can tell that it depends on X1. But in other cases, because maybe X1 and X2 are highly correlated, the OLS might, because of just random properties of your data, OLS might favor X2 over X1, and it might shrink the X1 coefficients down and weigh a little bit more heavily on X2, right? This is just something that happens with ordinary least squares. So, so this is where doing something like LASSO or ridge regression can benefit, okay? So yes, when you use LASSO, when you use ridge regression, it does push your R-squared values down, okay? And when you do LASSO or ridge regression, what happens is that you get biased estimates, okay? So that in the long run, when you take the expected value of LASSO coefficients or the expected value of ridge regression coefficients, those expected values will be different, will not be equal to the true coefficients that exist in the population, right? But the benefit, right? So you're taking on all these bad properties, right? Your R-squared goes down, you're gonna get biased estimates, okay? But the contrasting benefit is that the variance goes down, okay? So, so we're gonna get biased estimates, but we're able to reduce the variance, right? And so this is why we might want to do regularization, okay? And so, you know, why do I care about less variance? Okay, so less variance is a desirable trait of models, and what that means is that the model estimates that we have, okay, are less likely to be swayed by the noise that exists in the observed data, right? So, you know, every time you take a random sample, if the coefficients you fit change drastically with each random sample, then you can't be very confident in your current set of coefficient estimates, because you might just in the back of your head, you might say, well, you know, if I take a different random sample, my coefficients could change a lot, right? So if you have high variance in your coefficients or your model estimates, then you know that the values that you have are very much subject to the random sample of data that you have, okay? On the other hand, if the coefficient estimates that you get change very little from one random sample to another random sample, then you can be a lot more confident in your current set of coefficients, okay? So you can say, well, here's a random sample, and if I took someone else's random sample, you know what, my coefficient estimates barely change. So I'm pretty confident about the numbers I have, right? And so, you know, I think this is covered, I guess, in the 100C as far as the standard errors of your coefficients and things like that. But in general, you know, lower variance is a good thing as far as your coefficient estimates go. Okay, are we okay? Is this good so far? Give me a green check if this is good so far, what I'm talking about. Or give me a no if this is no good. Or questions. All right. Okay, about 2/3 of you said yes. All right, I'll take it. Okay, so what I'm going to do is I'm going to do a simulation study. Okay, and so we're going to simulate a population. Okay, so again, in the population, the true relationship depends only on x1 and only on x3. Okay, but x2 and x4 are correlated. x2 is correlated with x1, and x4 is correlated with x3, but the true values depend only on x1 and x3, right? And what I'm going to do is I'm going to simulate a bunch of random samples drawn from the population. So what I'm going to do is each iteration, I'm going to do maybe like 100 iterations. And with each iteration, I'm going to generate random noise to add, right? And so this is going to simulate the idea of you got a different random sample. So you took a different random sample, and every time you take a random sample, it's got random noise put on top of it, okay? And so here's my observed data that has the random noise, and I'm going to fit the three models. I'm going to fit ordinary least squares, I'm going to fit LASSO, and I'm going to fit ridge regression, okay? And for LASSO and ridge regression, I'm going to just go ahead and use the cross-validation feature, and I'm going to pick the model coefficients that correspond to kind of the largest lambda that still produces the minimum cross-validation score, okay? And then we're going to store all of these coefficients in a few matrices. And so this is what the code looks like just for doing the stuff. So these matrices are just places to store all of the coefficients from the different models I run. Okay, I'm going to just do 100 repetitions of this. And within each repetition in my loop, I'm generating a new random noise, okay? And so my observed y will change, okay? I've got the true y, which we determined outside of the loop, and we're adding noise every single time with every single iteration here. And then I fit an OLS model, and I extract the coefficients, okay? And then I fit a LASSO model using glmnet, and extract the coefficients from the LASSO model and store them into LASSO model. And then I fit a ridge regression model, okay, which is alpha equal to 0. So these are the ridge regression. This is the ridge regression model, and I extract out the coefficients from the ridge regression model. Okay, and I do this 100 times. And so I'm going to get basically 100 different model coefficients for different random samples drawn from the population. Okay, and this is what it looks like. Okay, so this is just I'm looking at the coefficient for the x1 variable. Okay, and so the true in the population, the true x1 variable, and the x1 variable has a coefficient of 3. This is the true value in the population. And remember, what we did was we fit, you know, models to our data with random noise. Okay, and so because of the random noise, these are the coefficient estimates from ordinary least squares, okay, we see it is centered at 3, right? So ordinary least squares, those coefficients are unbiased, which means that the expected value is right around 3, and that's indeed what we get. But because of the random noise, sometimes it thinks that the correlation, or not the correlation, the coefficient is higher, like 3.5. And because of random noise, sometimes it thinks it's a little bit lower, like 2.5, okay? This is the, this is kind of the sampling distribution of our W1 term, the X1 coefficient, when we did LASSO, okay? And we can see it is not centered at 3. The true value is 3, and it's centered a little bit closer to like 2.65, something around there, okay? And again, because of random noise, sometimes it estimates as high as, 3.2, sometimes as low as, I guess, 2.3, 2.2, it happened once, okay? And this is kind of the distribution of the X1 coefficient under ridge regression, okay? And we can see it's also biased. It's not centered at 3. It's centered somewhere lower, like 2.2. But then, what's the variance that we have here on these coefficients? It's a little bit less as well. Okay, and so when we look at the mean, right? So we fit the ordinary least squares model 100 times to just different random samples of data. So we we extracted different random samples where the true mean, or the true coefficient is 3. And if I take the mean of all of these 100 OLS models, we get something very close to 3, okay? And if I did this a million times, I would certainly get something even closer to 3, okay? And then here's the variance. The variance on that first X1 term for the coefficient is 0.06, okay? With the LASSO, okay? So somehow my thing is different. The mean is not 3. The mean is biased. The mean is 2.68. Okay, I get something different from 3. But my variance has gone down. My variance is only around 0.03. Okay, so I've reduced variance on my coefficient term, at the expense of getting a biased estimate. Okay, similar thing with ridge. This term got cut off. I'll have to adjust it. But basically, my bias is actually even bigger with ridge regression in this case, but the variance is also is lower here. Okay, is that all right? If we look at the x2 variable and we look at the coefficient here, okay. So remember, in the true model, the true values of y do not depend on x2 at all. The true coefficient for x2 in the population is 0. Okay, and with ordinary least squares, it is centered around 0. Okay, but because of random noise, sometimes the coefficient is as extreme as -1, sometimes as big as +0.5. Okay, is there a way to correct the bias? Yeah, not magically. Okay, yeah, you don't know. That's the thing, is you don't know what your bias is, okay? And I'll talk about the bias variance trade-off, but yeah, this is there's not like a magic answer to this. Okay, so with ordinary least squares regression, it is unbiased, it's centered at 0, but the variance says sometimes it's as low as -0.5, negative something, looks almost as low as -1. Okay, with LASSO, okay, a lot of times it has pushed everything down to 0. Okay, but again, because of random noise, sometimes it's not 0, and you get values like this. And here's the distribution for ridge regression. So ridge regression doesn't like when one variable has a high coefficient and the other variable has a coefficient near 0. So it tries to actually push the coefficients towards each other. So we get quite a bit of bias. We get these bias values are quite high at 0.5 or something. Okay, and the variance actually doesn't get reduced as much here in ridge regression. And let me just show you kind of the properties here. So with ordinary least squares regression, the mean is fairly close to 0, okay? And the variance is around 0.087, okay? It's a fairly large variance for this, this coefficient, okay? For LASSO, the mean is also close to 0, okay? There's technically a bias here that in the long run, the OLS coefficient will have a mean of 0, okay? Just maybe in our sample run of 100, we're not there yet, okay? With LASSO, in the long run, our mean would not be 0, okay? It'll probably be close, but not 0. But what you look at is this variance is way lower, 0.0087, okay? Whereas as far as the variance over here, it's 0.087, okay? So this is, the variance here is 1/10 of the size, okay, with LASSO, okay? And, you know, as far as ridge regression, there's gonna be a significant bias in the variance here, but the variance here will be smaller than the OLS coefficients, okay? I'll have to redo my slides to fit this, but that's what we have there, okay? Let me give you the second quiz answer. Second quiz answer is also E as in elephant. Second quiz answer, E as in elephant. Okay, well, I've got just a few minutes left. I probably don't have enough to get through all of these slides in the bias variance trade-off. So maybe I'll save this until Wednesday. Okay, but what we see here is that, you know, the advantage of using LASSO and ridge regression is that even though we get biased estimates of our coefficients, is that the variance of our coefficients will go down, okay? And this is kind of a key theme that shows up in a lot of these machine learning things, okay? So ordinary least squares gives you the unbiased estimators, okay, in that in the long run, the average of your coefficients will equal the population coefficients, but you're going to have a fairly significant variance as your models, as the random samples vary, the variance of those coefficients will you know, will be there, okay? LASSO and ridge reduces the variance, which is a desirable trait, okay? So that you can have more confidence in your current coefficient estimates, right? So, and given any one given sample, you'll have more confidence in your current coefficient estimates. I don't know, are there any questions on this topic so far? Do we feel okay about kind of LASSO and ridge regression regularization and how it plays a little bit into the bias variance trade-off? And I'll fully explore the bias variance trade-off, I guess, on Wednesday, okay? And we'll talk about this, this calculation here as far as the bias variance trade-off goes. So, yeah, I guess I don't want to start the whole topic here with just 4 minutes left, but we'll end there today, and we'll see you guys on Wednesday. And yeah, that'll be it. So so stay safe and healthy out there, and we'll see you guys on Wednesday.